Hello everyone, let's solve this LeetCode problem. Search in rotated sorted array. This problem is pretty unique because it uses binary search to search in an array which might be rotated at some point. So in this example problem, there's an array given called nums, and there is a number target that we need to search for. And there are there's a possibility that the values might be rotated. For example, 0, 1, 2, 4, 5, 6, 7. This array might be rotated right after 2. So in that case, the array might become 4, 5, 6, 7, 0, 1, 2. And um, it asks you to find a particular target value. So if we had a sorted array, in an ascending order like this, you could actually use either a linear search to go through each of the values and to see if the value is there. In the case, return the index of the value, the target value, or return -1 if it is not there. So a linear search gives you an order of n runtime, but because this is sorted, you can just check the midpoint and leave one side and just focus on the other and use binary search, and that gives you a runtime of order of log n. And logarithm runtime is way better than this. So this is way better. This is what you're shooting for. But in this case, the array might be uh, uh, rotated at some point, and we don't know that. And can you still find an algorithm that is logarithmic? You can definitely do a linear search, but logarithmic would be better. But can you do that? It turns out you can actually. So to do that, you have to just think about an example, 0, 1, 2, and here let's say you're looking for the value 0. On the left, the first example has a target of 0 that we're trying to just search for. And in this one, let's also identify the indexes of this value 0, 1, 2, 3, 4, 5, 6. It's always convenient to have this indexes written right above the numbers. At this point, imagine you want to just run some kind of binary search. It's also helpful to draw a diagram 4, 5, 6, 7. These values are going down, right? And after that, the next value is at 0, and then it goes up, and this is 2, and this is 4, right? And this is 0, this is 1, and this is 5, 6, and this value is 7. And if you have a diagram like this, you can actually apply logarithm binary search, but the question is how, right? So let's see if you can do that. Uh, Before everything, let's just make this a bit smaller so that we can fit them in the screen nicely. So this is the structure, right? So what you can do is at any time in binary search, you pick a midpoint. So between 0 to 6, you have to find a midpoint. Let's say if this midpoint is going to be here at 3. And to do that, let's switch the color to, let's say, yellow. And da, 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 we're switching the color to purple now. Okay, so you take from 0 to 6, you take a midpoint. There's going to be at 3, right? So index 3 out of all those values. And at this point, how do you know if you're going to just look at the right or left? So you have to just understand that whether you're on the left side of the rotation axis or not, that makes a decision. So here you can actually compare that with your left side. So if your array is defined as A, and if your current midpoint is greater than uh, greater than the sorry greater than the value on the left, which is basically going to tell you, hey, in this space, you are on the left side, right? Your current this value is 4 and your midpoint value is 7. So you're possibly on the left side. And if you're on the left side, you can make a decision. Hey, you're looking for a value within this portion between the mid and the left. In that case, if the value is right here, let's say our target is somewhere here, then keep the left side. If not, we'll just search on the right side. How do you do that? You have to check if your a left value on the left is greater or equal to your target, and your target is less than uh, the value at mid. If you or in one case by default you find that the midpoint value is the one you're looking for. Let's say your target was 7 and you are also exactly 7 here, right there. You just check the number and return that right away. But if it is not the case, then you have to think about the condition. This condition, if this is the case and your target is somewhere in this shaded array, so in that case, you can actually just switch your, so initially you had your right and the left on these 2, 0, and 6. But at this point, you can take your right and set it right before this midpoint. In that case, your right would be mid minus 1. Else, else you would actually just know that okay, the current value and at mid is not the same, so your LL you have to just look on the right side. So you can actually just do mid plus 1 for the left. On the other hand, if the whole thing is not true, then you know your midpoint is somewhere here on the right side of the rotation axis. And in that case, how do you know you look at the left or the right? So for that, you cannot uh, be sure about the left side, but you can be sure that, okay, I am trying to find a region. So if it is a midpoint, oops, sorry. If this is your midpoint, and I'm going to switch the color. So if it is current midpoint and you have a value, target value, somewhere between the right side and between the midpoint, then you can actually just remove the left section and focus on the right. So if this is the case and if it is on the left side, right? Else, we're on the right side. And on the right side, we are going to just check if this is in the shaded orange region. And how do you do that? So if your the right side value that you have is less or equal, sorry, not less. Right side value has to be greater or equal to current target value, and the target value has to be greater than current midpoint value. If that is the case, you can get rid of the left portion and you can take focus on this section only. So your left should be mid plus 1, right? But if it is done, if it is not the case, else in that case, you know that okay, your target value is not there. It's somewhere on the left side, right? On this side, it's not there. In that case, you can gladly say, hey, my right point is at mid minus 1. And at one point, there will be one single value if you use a binary search. And if the final value is not matching, you can stop. So at this point, the runtime complexity will be order of n. So with that, let's solve this problem with the answer we have in our mind and see how we can actually pass. This is the left side of the search region, and it's the right side of the search region. And we're going to confirm our loop runs until we have L and R equals same. And Every time we have to just find the midpoint. And if these numbers have the value that we're looking for, which can be checked using this condition, we just return mid in the index right away. Otherwise, if our numbers mid value is greater than numbers left value, in the case we know for sure that hey, we are on the uh, left side. And when you're on the left side, we can check the value of the target. Nums on the left side is less or equal to target, and target is less than our numbers meet. And we can be confident that this is true, uh, that we do not need to look at the right side. So right would be mid minus 1. If this is not the case, what do? Our left will be mid plus 1 because current value is already checked at the midpoint. So not the true. We just escape this portion and look at the other side. And if we're not on the left side, we know that we are on the right side, right? And if you're on the right side, this is so the first section in this portion is basically very similar to regular binary search when everything is sorted in increasing order. But this right side is a little bit different, right? That's where you need to pay the attention. So at this point, if we're just checking with the right side, numbers on the right is greater or equal to our target value, and our target is greater than the midpoint. What do we do in that case? We know that it is actually corresponding to this particular orange region, this region. So in that case, the left becomes mid plus 1. If it is not true, our right becomes mid minus 1. So we just look on the left side. And finally, our uh, loop stops when L and R are the same. And at this point, we have only one value, but we don't know for sure that if it is the target we're looking for. So you have to check that if this is equal to target, in that case, you return the index of that. Otherwise, you return minus 1, and that is going to give you the solution. So running the code, and uh, we missed we had a small error because we are returning before the right braces. Yep, all the cases passed. So if whether you're looking for 0 and 3, now you can actually just get rid of half of the array and efficiently search for the value you have. And let's submit. Oops, we had a wrong answer. So let's look for where we have the error. Um, hmm. Hello, you just saw the last submission failed for one case, and that is because I forgot that this should be when we are on the left side and comparing with the left, it should be greater or equal. And that means on the right side, if you're noticing the code, it should be actually greater or equal sign. And that way, if there's only one value, 4, 5, 6, and if your current value is 4 and the midpoint, uh, this is gonna capture that case. For example, you had 4 and 1, and if this is the input and searching for 1 is the target, in that case, it's a 0 and 1 index, and in that case, 0th index is selected because our midpoint finding this line is basically going to uh, do a floor division or round down. Is a rounding up, and in the case 4 is the value, and when it goes to this block, your current L left value is greater or equal to 0, right? If it is greater than 0, then it would actually not select this value, and it'll try to just do the right side. It's going to end up having a wrong answer. But in this case, your 4 is here, and 1 is down here. And if it is the case, there's, this is fully reached. It should have been 1 and 4, but because this is rotated, now this is 4 and 1. And in this case, this is are on the left side, right? So unless you have a greater or equal, it's not going to identify that this is on the left side. And everything else is actually the same. So to just fix that, I had to just add an equal. And if we now submit, it would actually pass all the test cases. And yep, it runs with 100% performance. And I didn't mention the space complexity for this one. The space complexity would be order of 1 because no matter how long, we're not storing anything. So finally, the time complexity is order log n, where n is the length of the given array. And that's it. Thank you so much.